Okay, so Alan, welcome back. So in the previous video we talked a little bit about basically the different calculations that go, basically the time calculations and amplitude related calculations to a sine wave. Now in this video what I will do is that I will show you essentially how you can do all of those, I'll show you those things essentially basically on some signal generators and oscilloscopes and that sort of thing. Okay, so essentially, first of all, let's talk about the difference between, okay, so first of all we need to talk about the difference between AC and DC. Okay, this has to be straight, something like this, so that you can see everything. So first of all, DC is basically usually created using a power supply. This is a DC power supply, for example, and then you can turn this knob, for example, and you can read the voltage over here. This is the output voltage that essentially comes on these two terminals over here. You get a negative pole, you get a positive pole, and then you have the voltage over here. That you can see that the voltage changes, and this is coarse and this is fine adjustment of the voltage, these two, and this is adjustment for current, right? And basically what we have here is the DC power supply, and of course you can measure the voltage over here on using a DMM, a digital multimeter, meaning that if I set this to, open this thing, if I set this to, for example, DC volt, for example to 20 volt, I can measure the voltage over here like so. For example, now you can see that the voltage over here, what I'm reading is 9.35 volts, is the same voltage that I read over here, right? So essentially what a multimeter does is that it shows you the voltage. Basically the voltage. It gives you a reading for the voltage at this point in time, meaning that the only thing that it shows you is the voltage right now, and of course it keeps updating the reading every, for example, a few times a second, and then it keeps changing. It basically measures the voltage again and again and again a few times in a second, and you will get a reading for the voltage over here, right? Now what this basically, there is another way of measuring the same voltage, and that is using a graph essentially. And using a graph, you need to use an oscilloscope. And in order to use an oscilloscope, so essentially what you will do is that, let me see, why is it? Okay, so this is a simple oscilloscope, 20 mega, I think 20 or 30 megahertz oscilloscope. That's the bandwidth on the oscilloscope, and then you can you can essentially, let me see if I can put my camera over here. Okay. Okay. Okay, then on an oscilloscope, essentially, what you will do, or what you can do, is basically need to set this up properly. Okay, on an oscilloscope, so essentially what I can do is that I can take the output of this, the output voltage of this basically of this power supply, and give it to this oscilloscope. And you can see that on this oscilloscope I have a coaxial cable like this, right? So I have a cable like this, and this cable essentially on one end of the cable is connected to the oscilloscope over here like this, and another end is basically this test lead over here. This test lead over here, and this test lead, you connect this tip of the test lead to the positive voltage, and this to the negative voltage, and then that way you can measure voltages. So I connect this, and essentially this oscilloscope has two channels. It has one channel, channel 1 and channel 2, and you can essentially make measurements on both channels, well, kind of simultaneously, because you have only a single beam over here, and this is a CRT screen, just like an old TV, something like that. There is a gun at the back of this CRT screen that basically is shooting these beam of electron at this screen, right? And so if you want to do this, if you want to use both channels simultaneously, you have to, the oscilloscope has to essentially divide basically the beam that is shot at this screen has to be basically divided in time, meaning that for some length of time, essentially the oscilloscope will be reading from this input for some length of time from this input, and then it switches back and forth in order to give you two outputs over here simultaneously. And I'll show you what I mean by that. So for example, let's say that you have basically, I have a signal generator, for example, over here. I have a signal generator over here. I can show you that. Okay, so let's say that basically I connect this cable to the output of this signal generator and set it to, for example, to some sine wave 10k times 0.8, let's say 1 times, that's 10 kilohertz, right? And give it to the input of this oscilloscope over here, and that's going to be one of my outputs, one of my inputs, or essentially. The other output I connected to, for example, another signal generator, which is essentially this thing up here, this signal generator up here, and I connected to, for example, 10k, that's 40 kilohertz or so. Now if I connect the output of the signal generator to a to this cable and come down here, and then I connect one test lead to the input of this oscilloscope, like that, channel 2, and then I connect. This is now essentially this is the output of the second signal generator, and this is the input of the second channel of the oscilloscope. I connect them together this way, and you can see that actually nothing, right? You can see nothing. So, and that's because basically I have set the mode to channel 1, and I can set the mode to channel 2, and you'll see another wave over here. So if I set the voltage a little bit lower and frequency change it a little bit, if I set this position to, I don't see really much here. So now this is set to ground. If I go to AC, now I can see my channel 2, which is essentially this input, which comes from the second generator on top on the left hand side. And if I go to channel 1, I see the other wave that comes from the signal generator, the first signal generator. If I want to see both of them, I can set this oscilloscope to dual mode, and now you can see that I see both of these waves at the same time, right? But the problem is that I cannot see, you see over here, basically this is the position, this is the first wave, and I suppose this is channel A or channel 1, which is a much higher frequency, and this thing over here is channel 2, which is a much lower frequency. And if I change the frequency over here, you can see that I can see only one of these at a time, and that means that the time base of this oscilloscope there is only a single time base, right? And so if I change the time base, it will be changed for both of these signals, and then at a time you can see only one of them. Now there are some oscilloscopes that have two time bases, for example, meaning that for channel 1 you can use a separate time base, for channel 2 you can use a separate time base, and then you would be able to see both of these simultaneously properly. But on this oscilloscope it's actually not possible. Usually on, for example, Tektronix oscilloscopes, you would see that sort of thing. So essentially now you can see that I have two outputs here, and this is the dual mode, this is channel 1, this is channel 2, and I can see, well, kind of, if the frequencies are not too far apart from one another, you can see both of them if you use the dual mode, essentially, something like this, right? So that's basically why you would need an oscilloscope if you were looking at two waves having many. I mean, if the frequencies were a lot different. Right now, basically, this is 80 kilohertz, this is 40 kilohertz. If I set the frequency over here to this is 10K. Let me go over here to 10K. And then again, this is 0.4, and this is 0.4, this is 4. So if I change the frequency here a little bit, then I can see both of these waves at the same time. But now, you see the frequency over here is, for example, this is channel 1, the frequency over here is about 1.4 times 10 is equal to 14 kilohertz. Over here is 40 kilohertz or so, right? So you can see both of these at the same time, and these are two waves that you can see over here. And this would be the first wave, this would be the second wave, right? Okay, so this is about And so on an oscilloscope and something like this, you essentially have something like this, which is the intensity, meaning that when you turn this down, your intensity goes down, the intensity of this beam of light goes down, the intensity here, this way it goes up, and you have to essentially adjust this in such a way that it doesn't hurt your eyes. There is the focus, you have to focus this in such a way that you get a crisp line over here. Then there is times x times 1 times 5, that essentially multiplies your amplitude by a factor of 5. Sometimes basically this knob over here is not sensitive enough, so you want to multiply by 5 so that you can see some waves better. We will get to that if we get a good example. Then using this, you can basically using these two knobs that says position, you can adjust the position of channel 1 and channel 2 on your screen. You can move them up and down like this, and this is the inverted form of the waveform. Now this works essentially only on channel 2, I suppose, not on channel 1. Okay. Then basically you have this knob over here, and you can see as I change this knob, the amplitude of the signal changes on the screen. Okay. And this basically, the way that you would use this is that you have essentially a volts per division over here. So this is 1 division, and this is, for example, this tells me now this is 5 volts per division. 5 volts per division is basically, that means that each of these divisions is 5 volts, meaning that if I center this, let me go to channel 1 for example, and center this channel around the baseline, and now if I go to AC, I can read this, I can see this signal over here, right? And this is now on channel 1, I'm on 5 volts per division. That means that the peak to peak voltage would be 1, 2, 3. Why am I moving down? Okay, it's very sensitive. Okay, so this basically means that I can read this peak, the peak to peak voltage 1, 2, 3, and 4 divisions approximately. 4 times 5 is 20 volts peak to peak is the signal that I have, and that is basically channel 1. So I can change the amplitude, of course. Over here I can make changes to the amplitude on the signal generator, right? So this basically tells us, this gives you less or more sensitivity based on the amplitude of the signal that comes in on this channel, meaning that if the peak to peak voltage of the signal that comes in is for example 2 volts, then you would need more sensitivity. If it's 20 volts, then you need less sensitivity, and then based on that you need to make changes to this, and you see that the more that I make it sensitive, the more basically my signal is jumping out of this on the top and the bottom of the screen, right? And you would not see it anymore. So that's basically that. And the same thing applies to this one. This is volts per division for channel 2. And on channel 1, essentially you have this key over here, the selector that has 3 basically, it has 3, you can set it to ground, you can set it to DC and AC. So now if you're looking at the AC component of a signal, you set this to AC. If you're looking at DC, you set it to DC essentially. And essentially this is supposed to be I don't know, DC offset. I don't know why I'm reading. Okay. Anyway, when you're looking at DC, you essentially need to set this to DC, right? That is basically this key over here, right? And then basically, for example, there is always some switch on your oscilloscope that lets you select between channel 1, channel 2, dual mode, and add, for example. There is, for different oscilloscope, you would see different things. Meaning that, for example, on this oscilloscope, as you can see, what I have, the way that I can choose channel 1 or channel 2 is essentially this thing over here. I can choose channel 1, channel 2, and then I can choose alternative, chop, add, and then this is for the time base, for example, right? And then this is for trigger, this is for, I think the dual mode on this oscilloscope would be the alt mode, if I'm not mistaken. But we need to turn this on and see how that works, if that's necessary. But on different oscilloscope, you can see that, for example, on this oscilloscope, the time base is over here. We will get to that. And the time base on this oscilloscope is, for example, this thing over here, this knob over here. Then basically these are the volts per division selectors. The volts per division selectors for this oscilloscope are over here. I don't really trust this oscilloscope that much, so I don't turn it on that much. And for example, this is 0. This is AC and DC on this oscilloscope. On this oscilloscope, they have put everything in one switch, and then it's becomes 0 and DC and AC, for example, something like that. Essentially, any oscilloscope that you have to just take a look at the front panel, and then you will recognize everything that most of the things that you see over here. Now, the next thing that we have here is, so essentially the mode switch, it allows you to select between channel 1, channel 2. Oh, you're not in the shot. Channel 1 and channel 2, and this is dual mode, seeing both of them come simultaneously, and this is the add mode, which allows you to add both the signals together, right? Add both of the signals together, and you would see a signal like this, something like this. Not very efficient, but well, okay. They have a circuit in this that adds both of these signals together. And then there is the trigger level. You can see that sometimes when you want to trigger on a signal, now right now you can see that there is no trigger here. You cannot see anything. Over here there is no trigger, but then you have to sometimes play with this so that you trigger on the signal so that you can actually read your signal. And this is your position, the horizontal position of your signal. This is calibrated or variable. Basically, these are not that important. These are the way that, I mean, you could, this is basically this time division, basically selector is calibrated to, for example, seconds, milliseconds, microseconds, and so on and so forth. Sometimes you need to fine tune this, so you make it variable, and then using this you can change this, and then you have to read the user's manual to see basically what this exactly means, because there's no numbers in here. Then you have to make a lot of approximation to see basically to make sense of basically your frequency and things like that. So you usually keep this calibrated so that you have no problems. And then over here, basically whatever time that you see over here, if you set this to times 10, then you would multiply it by 10 or something. In every oscilloscope these are a little bit different, but essentially the main things that you need to understand from the oscilloscope is the time per division, which is this knob over here, the time base, which is this is the volts per division, this is the time base, and this switch over here that lets you look at AC or DC, and basically this position over here and this position over here, right? And then there is the intensity and focus, you know what they are. There is this lets you change the slope, and then essentially over here, this is the mode, this is the trigger source, for example. The trigger source, essentially what you can do with this is that you trigger on dual alt or dual and alt, meaning on vertical. This is channel 1, external and line. So you usually set this to vertical dual alt, and that means that basically you're triggering either on channel 1 or channel 2, whichever one is present. This way you're triggering on channel 1, for example. This way you're triggering on this is external trigger. For example, you trigger on this thing over here. You can using a signal generator, you can inject some signal over here, and then you need to know what sort of signal, of course, to basically to inject in here. I don't really know what sort of signal you need in order to trigger this. And this line, it essentially triggers on the input line, meaning that the AC line that comes from the wall outlet, essentially. You can keep this over here. And then the mode over here is auto, norm, TV vertical, TV horizontal. These things you need to really read the user's manual. I think you keep this either on auto or norm in order to use the oscillator. The TVV and TVH are I think these two are related to those people who service basically TV sets and that sort of thing. This is something related to that to their world, is not that relevant to our work here. It's either norm or auto, I suppose. You don't change this really. So essentially that's basically how you use an oscilloscope. And over time, when you have an oscilloscope, then you will learn how to work with it. I mean, it's usually not really important to know exactly what these things do. For example, I really don't know how to use this variable mode over here. I never use it. Or for example, this TVV, TVH, that's not relevant to my work. I never use it. Sometimes, of course, for some purposes, then you might need to go into your user's manual and take a look at what these circuits essentially do. Otherwise, you don't really pay attention to them. And that's essentially that. Now, let's basically take the DC voltage that now I disconnect all of these inputs from the oscilloscope, and I have no input here whatsoever, right? And I go to channel 1 and adjust this on the baseline, and then the channel 1 I connected to basically the normal test lead, and like this, and now my test lead becomes essentially this thing over here, right? Now I connect this test lead to the voltage that we have from the supply voltage, the power supply. So I connect the positive to positive and negative to negative, and you can see that you see essentially nothing because my signal is actually going to ground here, right? Now if I look at this AC, I see nothing here, right? If I go to DC, you can see that I have 9.36 volts over here, and this is set to 5 volts per division, so I have 2 divisions over here, and this is above the baseline, right? So that's positive about, let's set this to 10 volts. Set this to 10 volts. .04 volts, and you can see that, well, I have never actually calibrated this oscilloscope, but it's pretty accurate. It's exactly 10 volts, and meaning that you can see that I have 2 divisions over here. 2 times 5 is equal to 10 volts. Is my voltage over here with reference to ground, of course, right? And the ground is basically this line over here, because I set the ground to this line over here. You can set the ground to any line, of course, but I set the ground to this line, so with respect to this line I have 10 volts over here, right? So this is essentially DC, and you can see that DC does not change over time, and this is time based. This is your time axis, and your time axis is controlled by this switch over here. Now, right now, I'm not sure if you can see this, but my time base is set to 10 microseconds, right? That means that each of these divisions, each of these horizontal divisions, is 10 microseconds. Is 10 microseconds, right? So that means that, well, and basically, as you go towards the right, time is going by, and each of these represents 10 microseconds, 10 microseconds, and so on and so forth. So you can see that your voltage over time stays constant. It doesn't change, right? So now if I switch to an AC signal, I connect the input of the oscilloscope to basically to this output over here, right? So I disconnect this over here and connect this output over here, and you can see that I have a AC signal, and the AC signal essentially is changing over time, meaning that from this point in time, basically from this point in time, the signal is changing, decreasing, negative, positive, increasing, and so on and so forth. That's essentially AC. Of course, you have to be on AC, of course, right? And well, of course, then when you are on AC, your time base is functional now, meaning that you can see that, for example, right now I'm on 10 microseconds, and this is my signal over here. And in order to be able to know what is basically my frequency, for example, you can see that from here, as we discussed in the previous video, at this point in time, you can see that the voltage is 0 and it is increasing. At this point over here, again, the voltage is 0 and increasing, right? So from this point to this point, you can consider this a a complete cycle, right? So if you take that as a complete cycle, then basically the time required for a complete cycle is called your period. And so if I want to read this, I reposition this a little bit so that basically the signal basically goes exactly through the junction, the intersection between these lines, so that I can exactly see what's going on here. And you can see that basically the signal at this point is going upwards, and at this point again is going upwards. So the only thing that I need to do in order to know the period, I need to measure this time basically on the oscilloscope. And now some oscilloscopes, they do have cursors, and you can put the cursors on the screen, and then they tell you basically this is the time interval, for example, between the two cursors. This oscilloscope does not have cursor. This is a pretty basic oscilloscope, and so you have to do everything in your head, meaning that to calculate, for example, what is the time, what is the period of your signal, you have to essentially read everything, right? So now let's do this one together. Okay, so now let's do all the calculations related to this, at least to one waveform like this. All the horizontal and all the vertical calculations related to this. So first of all, let's calculate the frequency of this waveform. So this waveform is essentially coming from here. And I can see that this is something like, for example, 1.4 times 10k. That would be equal to about 14 kilohertz or so. Okay. Now the way that you can see this is a frequency counter, and a frequency counter would be something like that. So if I use this frequency counter, I'm not really sure if that's very accurate. So I'm going to connect the same output. I mean the same output from the generator. I connect it over here. I'm going to get rid of this. So if I connect this over here, this tells me that it's 14.5 kilohertz. You can see that over here it says 14.5, and it's kilohertz over here. It's 14.5 kilohertz. Now let's see if exactly 14.5, 50.501. Now let's see if that's really accurate, because I don't really know. I have never actually used these practically. So what I'm going to do is that I'm going to use an oscilloscope that I have over here. So essentially another type of oscilloscope that you can use is something like this. You see this oscilloscope over here on this PC. So this is an oscilloscope. This over here is an oscilloscope. So it has basically the same two channels coming in, right? So this is channel 1 and channel 2. This is channel 1 and channel 2 of this oscilloscope. And this is the ground and some test signal over here for alignment and that sort of thing. And then on the back side you have the USB port that goes to a PC. And then on a PC you would be able to, there is software that you can install, and then you can use this on. So if I run this software over here, I can put this software over here, and then you can see that now I can connect the output, for example, to channel 1 of this. This is essentially a digital oscilloscope, and you can see that I have some reading over here. Now sometimes this is essentially, this is channel 1, right? This is channel 1, and so I've set that to 20 volts, for example, times 10, and then you can make changes. This is 1 second. So this is your time base. This is the same thing that I showed you, for example, on the actual oscilloscope. So I set this to, for example, something like, if we go to something about 10 microseconds, this should show us something, hopefully. And then I have to just make some changes to, this is times 1, for example, 10 volts, 5 volts. You can see that trigger source channel 1 sweep, trigger sweep auto, and trigger mode H. So you can see that I can essentially change the frequency here, the time base here, and but then the problem is that this is not, this is essentially not, this is 50 volt, 10 volt, 5 volt, 1 volt, 200 millivolt, and 50 volt. But for whatever reason, the amplitude is way too low, way too high for this. Let's change this to 1 and see what happens. Well, I'm not very much proficient with this oscilloscope, but essentially you can change, you can basically measure the frequency and the period, essentially the frequency over here, and it's 14 point, it's changing, jumping around, 14.7. It's about 14.7 kilohertz, right? It's either 14.3 or 14.7. So that tells us that essentially tells us that that essentially the reading is not that far off. Okay. It essentially tells us that the reading is not that far off. So now I can disconnect this signal from here, and if I go back to my I think I need to, if I go back to my let me displace this thing. Okay, so now I mean, for at least for the time being, I put this over here so that I can reach it, and so or I can put it even up here. I'll put this up here. Would be possible to put this up here. Okay. So So then basically again I can connect the signal up here and see what sort of frequency we have to the counter, and the counter tells me that it is 14.5 kilohertz. It's good enough. Well, there is no problem with that. Now let's calculate the frequency using the oscilloscope. So on the oscilloscope, essentially what you have is your signal up here, on the oscilloscope you have your signal up here. So you see that basically you see that one complete cycle occurs from here all the way up to here, between this point and this point in time. And so I can make some changes, move this around, so that again the wave goes through the intersection of these basically divisions. And so I have 1, 2, 3 point, and I don't know if you can actually see this, but each of these divisions, horizontal or vertical, is in turn basically broken down or divided into 1, 2, 3, 4, 5 equal distances. That means that if I take this as one division, then each of those equal distances would be 2/10 of a 0.2 or 2/10 of a division, 2/10 of a division, right? So that means that basically this is now 1, 2, and 3, 3.2, 3.3 horizontal distances over here. 3.3 horizontal distances over here, right? Now 3.3 horizontal distances, and the time base is set to 20 microseconds. 20 microseconds. So for such situations you usually need a piece of paper or a calculator. Now I don't have any of them right now, so let me get some at this one. Okay, so now let me write on the screen, that way that you could see me much better than this. Okay, so 3.3 horizontal distances, that would correspond to basically my time base is, as I mentioned, is set to 20 microseconds. So my time base is set to 20 microseconds, and I have the basically one complete cycle. One complete cycle essentially occurs in 3.3 horizontal distances. So that means that basically if one horizontal distance corresponds to 20 microseconds, then basically 3.3 horizontal distances would correspond to how many to how many seconds, and then your x would be equal to basically 3.3 horizontal distances times basically times 20 microseconds divided by one horizontal distance, right? You can cancel these two out, and you would be left with simply 3.3 times 20 microseconds, which is the same thing as 66 microseconds. So that means that basically 3.3 horizontal distances on the oscilloscope right now is corresponding to 66 microseconds. That means that, which basically means that your period is equal to 66 microseconds. And in order to calculate the frequency of the signal, the frequency would be equal to basically, okay, now in order to calculate the frequency, what you can do, let me calculate this again. So in order to calculate the frequency, what you can do is that you know that frequency is basically 1 over period, which is the same thing as basically 1 over essentially 66 into 10 raised to the power negative 6 in seconds, right? And 1 over 66 is the same thing as 0.01515 and so on and so forth. I take two significant figures, for example. I take it as 0.015 into 10 raised to the power 6 seconds, which I can write as so over here basically I can write this as basically 0.0 I'm sorry, I can write this as basically 15 into 10 raised to the power negative 3 into 10 raised to the power 6 seconds, and now of course that this would be of course in hertz, of course, right? Made a mistake here. This would be in hertz, of course. So this would be basically in hertz, right? And so this again would be in hertz, and so this would be basically 0. Actually, I'm going to write this as basically 15 into 10 raised to the power negative 3 into 10 raised to the power 6 hertz, which is the same thing as 15 into 10 raised to the power basically 3 hertz, which is basically 15 kilohertz. And the reading that we had over here, the reading that we had on the frequency counter was exactly 14.5 essentially kilohertz. So, and in the calculation we got 15 kilohertz, right? So of course when you read something on the oscilloscope, of course you have some tolerance over here, because basically this line, I mean there is no better way of reading this line. This is the best way that you can essentially read this line. And this type of oscilloscope is not for exactly to be completely accurate. If you want to be accurate, you have to use a digital scope that tells you all of the different all the numbers. It gives you the cursors. You can throw in all the cursors on the screen, and you can make accurate measurements and that sort of thing. This oscilloscope is essentially something like, for example, this multimeter over here. Something like this multimeter over here. When you use this sort of multimeter, you don't care for accuracy, you just want to see how the needle is playing, how the needle is going back and forth. For example, when you're looking at some voltage or some current or something like that. When you want more accuracy, then for example, you would use some meter like this, right? So that's essentially that. But you need to at least be able to make approximations on this scope, and you need to of course understand the meaning of basically what is the frequency, what is the amplitude, and everything and things like that. Now one more thing that we need to basically calculate here is essentially how to how to calculate the amplitude, the V of basically peak to peak, the V of peak, and V of RMS related to the same signal. But I guess I'm going to end this video here, and then in the next video we will make some voltage readings, V of PP, V of P, V of RMS, and then we will also talk about an RMS meter and make some measurements using this RMS meter as well. I'll see you in the next video, and thank you.